So the first law of thermodynamics is the law of conservation of energy. Energy cannot be created or destroyed in a chemical reaction. The total amount of energy in the universe is constant. We sometimes refer to this as there is no free lunch. You can't get something for nothing. You can never design a system that will produce energy without using energy. It's not possible. People have tried. You're welcome to devote the rest of your life to trying, but it's just not going to happen. With energy, you cannot get something for nothing. So now we have to talk about state functions. We'll use altitude as an example. So if we look at the elevation of a person at any point during a climb of this mountain, their elevation is a state function. A state function depends only on the difference between the initial and final values. It does not depend on the path taken. So let's just talk about the beginning and the end of the hike here. There's two paths. There's path A, which is 12 miles, zigzagging up the mountain. And then there's path B, toughing it out and just going straight up. And that's going to be 5 miles. You start at the bottom at 0 feet elevation. You get to the top, 10,000 feet elevation. So a person going on path B has traveled 5 miles. A person going on path A has traveled 12 miles. But their elevation is the same. It doesn't matter how they got there. They're still at the same point above sea level. The distance they travel is not a state function. The distance does depend on the path taken, but the altitude does not. Does anybody have any questions about that? The internal energy of a system, we use E to stand for that, internal energy. This is the sum of the kinetic and potential energies of all the particles that compose the system. So this is all the types of energy that the particles within the system have. That's called the internal energy. Internal energy is a state function. Its value depends only on what state the system is in. It doesn't matter how it got there. And state functions are important because they simplify our calculations and thinking about things. Because even if we know that the process by which someone went, or let's just go to this example. Say someone took their own path, call it path C. Do we know how far they traveled climbing the mountain? No. We don't know their distance unless they were wearing a pedometer or something, or measuring it with a tape measure. But we can still tell that if they started here and they ended up here, they've achieved an elevation change of 10,000 feet. It doesn't matter how they got there. And so that makes calculations easier. So internal energy is a state function, and so we can look at the change in internal energy is the final energy minus the initial energy. So this symbol delta, it looks like a triangle because it is a triangle, but that's a capital Greek delta, which is sort of a D. That means change in, and it almost always represents the final value minus the initial value. And so we'll see delta show up again several other places. So the change in energy is the final energy minus the initial energy. In a chemical system, we can think of the reactants as the initial state and the products as the final state. So this is an energy diagram it's a very simple diagram, but it helps us make a picture out of some very abstract concepts. And I don't know about you, but I find it easier when I can see things. I need to see it, and then I can understand it. So we use diagrams like this to help us visualize what's going on. So we're representing the internal energy of the system is being higher as it's going up the page. So here are our reactants, carbon and oxygen. Those are the two reactants. And these have a certain amount of internal energy. When they react and form CO2, the CO2 has lower internal energy than the reactants did. And so CO2 is on a line that's lower, and we see that there was a change here. The change in internal energy is negative. The final energy is less than the initial energy. So small number minus big number is a negative number. What that tells me is that the system, this chemical reaction, lost energy. That energy didn't disappear, it had to go somewhere. It went into the system. The surroundings. So the system had some energy, and after the chemical reaction, it has less energy, and the energy it lost went into the surroundings. It's like money, right? So you had a $5 bill in your wallet, and it's not there anymore. What happened to it? Well, maybe you spent it, right? Maybe you dropped it on the sidewalk. Does it still exist? Yeah. Even if you don't know who has it right now, it's still there. Somebody has it, right? Money just doesn't cease to exist. Energy doesn't cease to exist. It just gets transferred. So the energy diagram is showing energy changes much like an altitude diagram for a climb. Yes?
Can the reverse of this be true?
Yes, the reverse of this can be true. In fact, it's true on the next slide. So this is like people coming down the mountain, right? We can establish the initial energy of the reactants, the initial internal energy of the products. We can measure this change. Exactly how it happened doesn't matter. We can do the opposite. Wait a minute. Yeah, this is just more of the same. I fooled myself. Sorry, I'm taking cough medicine, and it makes my head float above my body, so today's not going to be really great. So the reactants had more energy. Energy is lost by the system, so the change in energy is negative. Energy is lost by the system. That has to be gained by the surroundings. What's negative for the system is positive for the surroundings. If I give Sushil a $5 bill, that's negative for my wallet and positive for his wallet. If he gives it back to me, that's negative for him and positive for me. So these sign changes or sign conventions for energy are just like money. It's like transferring money between accounts or between people. Here's the reverse. So here, this is the same chemical reaction but written backwards. So we're taking CO2 and breaking it into carbon and oxygen. CO2 has lower internal energy than carbon and oxygen do. I'm not going to talk about why right now. So if we go from CO2 to C and O2, then there's an increase in internal energy. In order for this reaction to occur, energy comes into the system from the surroundings. And this has gone up in energy. The change in energy, final minus initial now, is greater than 0. It's positive. Yes?
Is that typically how it works for oxygen and carbon dioxide? So you need like an input of energy to create oxygen, and carbon dioxide is going to form like as less energy?
Yeah, so the relative internal energies of carbon, oxygen, and CO2 are always going to be like that. What we're going to see is that the energy change can be positive or negative for a reaction occurring. A spontaneous reaction will happen on its own, but you can often make the reverse reaction happen by either putting energy into it or taking energy out of it, whichever is appropriate. So here, the change in energy for the system is positive, the change in energy for the surroundings is negative. These changes in energy are the same number. One's got a negative, one's got a positive. Okay, and an equation like this, I think maybe because it's just so simple, students have a hard time understanding what does this mean? So if the energy for the surroundings, don't write with the highlighter, that doesn't work very well. If the energy for the surroundings is 5 joules, then negative delta E we've got negative, they're opposite of each other. So whatever this one is, you put a minus in front of it, and that's what this one is. I've never done that exact thing before, and I don't think I liked it. So summarizing energy flow. If the reactants have higher internal energy than the products, the change in energy for the system is negative, energy flows out. If the reactants have a lower energy than the products, then ESIS is positive, energy flows in. So energy is like money, the system is like your bank account. So money leaving is a withdrawal, it's negative. Money coming in, a deposit, is positive. So let's look at this, see if we understand what we're talking about here. So consider these fictional internal energy gauges that describe the initial conditions for a chemical system and its surrounding. So here's the chemical system and here's the surroundings. Which of these three, A, B, or C, sets of energy gauges corresponds to the final conditions following an energy change in which delta E system is negative? The change in energy for the system is negative. So if delta E for the system is negative, did the system gain energy or lose energy? It lost energy. So the energy bar for the system must be smaller than it was before. So we can rule out which one? C. Because in C, the system didn't change at all. If the change in energy for the system is negative, then this bar has to get smaller. So for both A and B, the system bar got smaller. If the system bar gets smaller, where does that energy go? It goes into the surroundings. So the surroundings have to increase by a corresponding amount. So what's the correct answer here? It's A. One goes down, the other goes up. We don't have a situation where I buy something from you for $5 and you don't get the $5, and I don't have the $5 and the $5 disappear. That doesn't happen. Any questions? So heat and work are ways that energy can be exchanged between the system and the surroundings. So we've got the system that we're interested in, the surroundings, everything around it. Heat can go either way. Work can go either way. Work is abbreviated with a W. That makes sense. Heat is abbreviated with a Q. I didn't make this up. It's just what everybody does. So Q and W. The change in energy is a state function. Q and W are not state functions. Their values depend on the process. So here's a summary of sign conventions for these things. The change in energy is equal to the sum of the heat and the work. So heat is positive when the system gains thermal energy. It's negative when the system loses thermal energy. Like if it's positive when money comes into my account, it's negative when money goes out. Work done on the system is positive, work done by the system is negative. So this is how I think about that one. It's like, so I'm doing work, I am the system, and I'm doing work for somebody else. I'm mowing the lawn and raking up all the leaves. Do I feel real positive or kind of negative about that? Negative. It's a lot of work, right? It's an expenditure for me. I don't really want to go do that. I've got my own stupid yard to take care of. Work done on the system. You could also think of work done for the system. That's when somebody comes and cleans up my yard for me. I like that, right? That's a positive for me. I'm gaining the efforts of their labor, right? So work done on me, done for me, is positive. Work that I do for someone else is negative. And the change in energy flowing into the system is positive, out of the system is negative. So back to those billiard balls. Here we have the white ball, and it's rolling across the table. It has kinetic energy due to its motion. Its initial kinetic energy is 5 joules. As it rolls across the table, because this is a real-life situation, there is some friction on the table. That ball will not just roll indefinitely at the same speed, right? It will slow down due to friction. So as it rolls across the table, it's going to lose some of its kinetic energy due to friction with the table. We're going to say it's losing half a joule of energy. So by the time it gets over here, it has 4.5 joules of kinetic energy left. It can transfer the 4.5 joules of energy to the purple ball, and now the purple ball leaves with 4.5 joules of energy. This transfer here is work. This is heat. Heat, energy is lost through the friction with the table. Here, work is done on the ball, and now the kinetic energy of the white ball is 0 at the end. In this example, the system is the white ball, and the surroundings includes the table and the purple ball. So the energy lost by the white ball is gained by the surroundings. Any questions? So the change in energy here is negative 5 joules for the white ball. It's positive 5 joules for the system. What if we have an abused pool table? Or maybe a really cheap one. It's a rough table. The ball does not roll as well on a really rough table, right? Think of rolling a tennis ball on the sidewalk versus rolling it through long grass. Right? It just doesn't go as well. A lot more friction. So here, the ball originally starts with 5 joules of energy, but as it's rolling across this rough table, it loses more to heat, 3 joules. When it gets here to do work on the purple ball, it only has 2 joules left. And so it does the energy transfer there through work, and it's left with 0. The purple ball goes on its way. So the work now is 2 joules, and the heat is 3 joules. So the work and the heat are different than they were in the previous example. The change in energy for the white ball is the same. In either situation, its change in energy is negative 5 joules.
Why is work negative?
because the system, the white ball, lost the energy. It had 5 joules of kinetic energy to start with, and now it's sitting there and has 0 joules of energy. And the energy didn't disappear, it got transferred as heat to the table and movement of the purple ball. So this went from 5 to 0, and so delta E for that is 0 joules minus 5 joules, which is negative 5. The system went from 0 to plus 5. So this is, the surroundings. This is the system. The surroundings end up at 5 joules, started out at 0 joules, and so their change is plus 5 joules. Any questions? These two numbers fit this equation. Delta E system equals negative delta E surroundings. That does not mean that the change in energy for the surroundings is negative and the change in energy for the system is positive. Here the change in energy for the system was negative, so that was negative 5 joules. And that is equal to the negative of the change in energy for the surroundings, which was positive 5 joules. All this equation means is that they are the same but opposite in sign.
So then it would be the loss in efficiency?
Yeah, the heat that's lost, the energy that's lost through heat, usually that energy is not useful. And so when we're talking about mechanical processes and we're talking about efficiency, we've got, say, like with your car, you have energy stored in the gasoline. You burn the gasoline, it releases energy. Some of that energy gets used for motion, but a lot of it gets dissipated as heat. We say that it's lost, but it's only lost to usefulness. It still exists, it's just lost to usefulness. So change in energy for the white ball is the same for both cases. Change in energy for the surroundings is the same in both cases. But Q and W are not the same, because Q and W both depend on the process. Any questions? A cylinder and piston assembly, defined as the system, is warmed by an external flame. The contents of the cylinder expand, doing work on the surroundings by pushing the piston outward against the external pressure. If the system absorbs 559 joules of heat and does 488 joules of work during the expansion, what's the value of delta E? Okay, this is actually a very simple math problem, but it requires understanding of what all these words mean. So pulling out the numbers and writing them down, we've got 559 joules, and we have 488 joules. This is joules of heat, and for heat we use Q. And this is joules of work. Work is W. Now we have to identify, are these values positive or negative? The system absorbs 559 joules of heat. Is that coming in or going out? Coming in. So it's positive. This is positive. We don't necessarily need a positive sign, but I'm just going to emphasize that it's positive. And again, it's so easy to get these things backward. Think about money. Because we're really good at thinking about money. You immediately know if if I make a deposit, if I put money into my account, is that positive or negative? Duh, that's positive. So energy absorbed as heat is positive. It's doing work. That's negative. It's not having work done on it or for it. It's doing the work. That's negative. It's putting out. Any questions about the signs on those two things? So to find the change in energy, the change in internal energy is the sum of the heat and the work. So 559 joules plus negative 488 joules. $71 joules. So overall, did the system gain or lose energy? It gained. This is positive. Okay? The change in energy for the system is positive. It gained energy. Its bank balance went up. Any questions?